questions from anything you've done in equilibrium so far? Was that a yes? About equilibrium, any questions? Yes. A typo, yes, let's deal with that. Page 15, question 4. Oh, yes. Yes, 4 and 5 repeat themselves, so that's 2.1c. Okay, and so question 5, I would assume that, let's get rid of this and make it less than. Okay, so we have 2 different questions now. Okay. And are we good with everything else, or do we have any other questions? Yes. On that same page. Page 10, question 3. We're going to post that for you, okay? Are we good with that? We're good with that? Okay. Now let's go to page 10, which is the 2.1b. Question number what? 3. What are 2 things that are true of both the forward and reverse rates at equilibrium? They are constant and they are equal. Yeah? Yeah. Yes. I am recording. Thank you very much. Yes. 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 Yeah, it's generally like whatever you put in at the beginning is your reactant, but like it's almost arbitrary. You could write the equilibrium this way, or you could write it that way. No, you can switch it around. Okay, so it just depends on the way it's written, what you'd classify as forward and reverse. Yeah. Anything else? Alrighty then, we are moving on to 2.2. Oh, something else. Yes, sorry. 20. Okay. 2 definitions of dynamic equilibrium. Well, let's see. Oh, look, on page 18, if you look, there's a box that says dynamic equilibrium, and it says 1 and 2. So let's take a look at those. That's 2.1d. Okay, here we go. So definition number 1, a system in which the macroscopic properties are constant, but changes continue to occur at the microscopic particle level. Now, people will say microscopic. I would argue that particle level is a better term because you can't really see the particles under the microscope either. Okay, but you will hear the term microscopic from time to time. So definition number 1, macroscopic properties are constant, but changes occur at the particle level. Definition number 2, a reversible system in which the forward and reverse reactions continue to occur at constant and equal rates. So how do those two relate to one another? Have a chat with your neighbor about that. Hmm? Good. All right, what do you think? Adriana? Yeah, the fact that they are constant and that they are, I mean, how would they be Yeah, constant accounts for the changes continuing to occur. Equal accounts for the macroscopic properties remaining the same, because if they are equal, you're not going to be making more of any one substance. So if something was colored, the amount of colored stuff would stay the same. Is good? Cool. Any other questions? Okay. So you would all be able to tell me 6 characteristics of a dynamic equilibrium. Would you? Tell your partner 6 characteristics of a dynamic equilibrium. All right, what we got? Yes. Temperature is constant. Yep. Yep. Closed system. Yep. Rate of forward equals the rate of the reverse or backward reaction. Both reactants and products are present. I mean, it seems obvious, right? But, pardon me? I didn't catch the words in between reactants and, you have reactants and products. Yeah. Okay, cool. Yes. Do you like the microscopic changes? By the way, if you're writing on an AP exam, I would not write something like that. okay? You know, actually write the real word. And number 6. Yes. You can start from either side. You can put reactants in and reach the equilibrium. You can put quote unquote products in and reach the equilibrium. Sort of, but you know, it depends on which direction you write the reaction. Like I said, if you've written the reaction so that B is the products and you put some B in the system, then you can approach it from the products. So, yeah, whatever. Okay, excellent. So let us go to page 24. Quick review, color is an example of what type of property? Macroscopic. And macroscopic means that a property is observable. Now, at equilibrium, if you do want to use abbreviations on the AP exam, make sure that you do the definition for the first time you use it. Then you can use it throughout that one question. Now, bear in mind that different people mark different questions, so if you do it in different questions, you would have to redefine each time you do a new question, okay? Not that it happens that much, but anyway. At equilibrium, macroscopic, properties are constant. And at equilibrium, I don't even know why we're bothering to fill this in, but you know, what is equal? Forward rate and reverse rate. A system at equilibrium will remain at equilibrium unless it is stressed. A stress is any change we make to the conditions of the system. The key thing is that it needs to make the forward and reverse rates unequal, okay? Stresses, when we are graphing them, are considered to be instantaneous, even though in real life they are not instantaneous. It makes graphing them much easier. So if something takes no time at all, how does that work on a graph? Straight up and down, yes? Okay. So on a concentration graph or a rate graph, these stresses will show up as vertical spikes. So if we have here concentration, and let's just say we have some NO2 and we have some N2O4, if, and this is our time, if at time t, whoops, that's the wrong place to label that. If at time t we add some NO2, the concentration of the NO2 will do what? Will spike. Okay, so we get that little spike. Now on a rate graph, any rate graph, you're going to have a forward rate, and you will also have a reverse rate. Okay, so we have a forward rate and we have a reverse rate. If you don't have two different colored pens, you can just do a dashed line and a solid line. And before we stress the system, Before we stress the system, what can we say about the two rates? They're equal. Okay, so our forward rate and our reverse rate are equal, and because it is really hard to draw them right on top of each other, we draw them just, as close as we can. Okay? Now let's say that our reaction was 2 NO2 in equilibrium with N2O4. If at time t we add some NO2, what would that look like? The forward rate would go up. What would happen to the reverse rate in that moment? Anything? No. Okay, so that's our spike. So what kind of things can be stresses? If we're going to make those two rates unequal, it has to be something that does what? Changes the rate, okay? And it has to change either one of the rates only, or it has to change both rates, but by a different amount. So if we change a concentration, that will only affect the rate where that thing is a reactant. Okay, so it'll either, if I put in a product, it'll affect the reverse rate. If I put in a reactant, it will affect the forward rate. If I take away a product, it will affect the reverse rate. If I take away a reactant, it will affect the forward rate. Is good? Yes? Don't worry, we'll do examples. If I change the volume pressure, that will actually change it'll change both sides if both have gases. If you only have gases on one side, it'll only change that rate. So we'll look at that a little more closely later. A change in temperature, do you remember which one is affected more? It affects the endothermic rate more. We were kind of looking at this morning. Maybe I'll draw it on here. If I have a curve like this, okay, and I have my reaction, that would be my activation energy of the endo or exo? Of the exo. Now going from here up to the top, that would be the activation energy of the endo. So always the activation energy will be greater for the endothermic direction, okay? Yes. Yes. Yeah, so you're going to be, yeah, you're going from a position, when you're going endothermic, you're going from a position of more stability to a position of less stability. Yep. Okay, so let's say that this is the activation energy of the endo. And let's say that this is the activation energy of the exo. Now let's make this really, really obvious here. Let's make it cooler. Do you see how we've almost completely disappeared on the endothermic reaction in terms of if I cool it down, there's almost no collisions or molecules that have sufficient energy? Does that make sense? Okay. You don't actually need to be able to draw this or understand it or anything, but it helps explain why, and sometimes you want to know why. Yes? But you're not going to have to be able to explain it. Yes? Hmm? It's with temperature, so temperature affects the endothermic rate more. Concentration, you'll only be affecting one direction anyway, because you'll have, if I put in NO2, I'm only affecting the forward rate. If I put in N2O4, I'm only affecting the reverse rate. So when I change a concentration, and we're not going to be like, oh, I'm changing the reactants and the products. So it doesn't matter whether it's endo or exothermic if I'm changing a concentration. It depends. There's other factors involved like entropy. Yes. So okay, now things that are not stresses. Not stresses. Adding a catalyst, it speeds up both reactions equally. Speeds forward and reverse equally. Yes? I don't know, that's how it is. I try not to think about it too hard because it makes my brain hurt. Okay? Plus, I'm not really good at drawing the diagram, so I don't know if I'm making the curve look correct. So let's just go down to our diagram in here and see. Okay, so if we add a catalyst, let's just do a quick diagram here. So here is our original EA endo uncatalyzed. Here is our EA exo uncatalyzed. Now this one is going to decrease by that much. And this one's going to decrease by that much. And I have trouble visualizing which one, like in terms of, you know, the area under the curve has changed by more, but I have been told that they have increased or decreased, or sorry, the amount has increased by the same proportion. And I'm going to believe that the people who have done the math, like actually done the calculus around this, I'm going to believe that they know what they're doing. So even if I cannot visualize it perfectly, I'll say, okay, I believe you people who have done the math. Okay? When your brain is like mine and your math is like okay up to a certain point, but then you're kind of like, okay, I've forgotten it all, or maybe I never learned it properly, then you just kind of go, I'll believe the people who do the math. Yeah. Okay, so catalyst speeds up the forward and reverse rates equally. Surface area also speeds up the forward and reverse rates equally. It just provides, you have more area on which the forward rate can occur, you have more area on which the reverse rate can occur because you'll be going between phases. Okay, so you've increased the surface area for the forward, you've also increased the surface area for the reverse. Often this will be something like where you have like a pile of solid, okay, and it's busy turning into ions. Okay, and then those ions are busy reforming solid. Okay, so you get ions coming off, you get ions going down, you end up with a constant concentration of ions. If you have a little tiny pile of solid, you'll have less dissolving and less precipitating. Yes? But if you have a bigger pile, you'll have more dissolving because there's more places where that can happen. But every time one dissolves, another one has to precipitate, so the rates will remain equal. Okay, so forward and reverse rates are speeded up equally. And finally, adding an inert gas. What does inert mean? Non-reactive. Helium, krypton, neon, any of the noble gases, okay? Yes? You might have, like, there might be a particular reaction where nitrogen is not involved in that reaction, and it could be inert in that case, but for you to know for sure that it won't react with anything in there, they're always going to give you a noble gas because it's like, you should know that noble gases don't react with anything. Should you know that nitrogen doesn't react in a specific instance? No, that's not it. You're not expected to know that. Yeah? Okay. Why are we doing that? Didn't we just do that? Okay, so we're going to skip that. Oh, why adding an inert gas? It doesn't do anything. Like, you get particles. It's the same reason why adding an inert gas does not speed up a rate. You can't speed up a rate by, it doesn't speed up either reaction. It does not change the rate. Okay? Because particles will bump into an inert gas, but sometimes people think, oh, there's a particle over here waiting to react. Okay, this particle over here is waiting to react. I'm gonna have to put it down because I don't have hands. With this thing here, and this one, oh oh, it bounced off and now it's not going to hit that. But guess what? Maybe over here, there's another particle. It bounces off and it hits that one. So it doesn't matter that there's other particles getting in the way. Quite frankly, with gases, it's mostly empty space anyway, so it really does not affect it to any great extent, okay? Or to any extent. Okay, we're gonna skip this because we just did that. You can try and fill it in later, just to like, as a review to think about it. Let's talk now about a shift. The shift is a response to the stress. The shift is a response to the stress. A system shifts in order to make the forward and reverse rates equal again, okay? Unlike a stress, which is instantaneous, a shift always takes place gradually over time, okay? So we will see a curve, all right? Now, shifts are fast at first because the difference in rates will be the greatest at the beginning. And they will slow down as time goes on as the rates become more equal, okay? So the shift is fast at first, which means that the curve will it be shallow or steep at first? It's going to be steep, and it slows down over time, and so then it will become more shallow. So we get a initially steep curve, more shallow over time, and finally it becomes flat, okay? So here we would have a rate diagram. So rate is on the y-axis and time is on the x-axis. We have our forward rate, we have our reverse rate. Initially, they are equal. Now, would you like to have one of the rates increase or one of the rates decrease? Let's have one of the rates decrease because we already had an increase, right? So let's just say that we remove some product. Perhaps we can precipitate, condense it out. That's one of the things you can do is if you cool the system, you can take a gaseous product, condense it out, and then its concentration will go down. So we remove some product, okay, right there. If we remove some product, which rate will be affected? The reverse rate. And will it go up or will it go down? Down. Why? There's less particles, therefore less collisions. Yes. Okay, less particles, less collisions. Now, that was our stress. What should our shift look like? Tell your partner what should happen to the red line and what should happen to the blue line. Okay, what do we think? Oh, sorry, you're still discussing. Okay, so it should look like this. I'm going to draw this part first because I want it to be in the middle. Yes, that'll make my life a little bit easier. Now I just have to aim for that when I'm drawing the curve part. That wasn't really in the middle, was it? Anyway, close enough. Here, well, that's not bad. Okay, so here we have our initial equilibrium. Then we have our stress. And then in here, what's happening in this yellow portion? This yellow portion is the shift. And then finally, what do we have when the lines are equal again? We have a new equilibrium. Now, one thing I would like you to take notice of is that, where could I draw this that it would be good? Okay, over here. We do not see this. What's wrong with what I've drawn there? Tell your partner, what's wrong with what I've drawn there? Okay, let's assume I don't make it flat there. Let's assume I do a better job of that. Let's. Okay, let's assume it ended up in the middle. I'm not very good at drawing. Yeah, let's just say it has to. I mean, technically probably not, but just go with that. What's your rate of change here? Slow rate of change. Is delta okay for change? Okay, slow rate of change. And then we have a fast rate of change. And then we have a slow rate of change. So is that what happens? No, it should be fast and then gradually get slower and slower and slower until it becomes 0. So this part here is wrong. The fastest rate of change is at the beginning. You want it to be steep and then gradually shallower and shallower. Yes. I mean, technically it would take some time, but we pretend that it doesn't for the ease of graphing. Okay, it's like a construct that just makes our lives easier when we're putting pen to paper. Okay? Okay. So here is a sample problem. I would like you to label the old equilibrium, label the stress, the shift, and the new equilibrium. And then you're going to answer these questions. And I'm going to make a note that I need to correct the spelling of reverse. Reverse. Oh, look, it doesn't have to meet in the middle. Yes. Oh, like, you mean that it's not in the middle here? Yeah, yeah, it's okay. I think, again, for your ease of graphing, you can just always make it meet in the middle. People who know what they're doing and what the particular reaction is can make the rates change appropriately. It will have to do with the stoichiometry probably, and perhaps also the endothermic exothermic, but that's beyond the scope of this course. Maybe, I don't know. I'm not going to worry about it. I'm going to give you that answer for now, and maybe we'll come across something. So for now, just don't worry about it. I know that's not very satisfactory, but that's where we're going. Okay. Hi.
Sorry to interrupt. I just thought like, oh,
Are you going to close the door behind you, Mr. Leung? No, you're just going to leave it open? Oh my goodness. Bye. Okay. Alrighty. Have we finished the questions? Yes? Do we need to go through them or are you good? You're good? Okay. Sample problem 2. Once again, label the old equilibrium, the stress, the shift, the new equilibrium, answer the questions, and then you're going to tell me what was the stress. Hi, thank you. Dayun is not here. Ooh, I got another question for you to add on to the end of this as well. There's a lot of chitter chatter. Are we discussing the question? Good. Okay, keep discussing the question.
That's what I put. Macroscopic as a surface. Okay. Well, I don't think it's. I got you. Roasted, but I'm
Okay, are we finished or do we need another minute? Nobody's saying anything, so I'm assuming we're finished. Do we want to go over any of the answers? Yes. The last two, let's go over the last two. I like the last two as well. What was the stress? Yes. Yeah, it was an increase in the concentration of NO. Okay? Because we see, oh look, NO increased. Yes? Now, which substances are on the same side of the equilibrium arrow? Cl2 and NO. There's a couple ways you can tell. What's one way you can tell? Yes. Yeah, I mean, there's no way that you could have NOCl plus Cl2 becoming NO because the Cl would just disappear, yes? Okay, so that's one reason. What's another reason you can tell that they're both on the same side of the equilibrium arrow? Yes? Yeah, they're both decreasing. So they would both have to be, say, reactants, or they would both have to be products in order for them both to be decreasing. Okay, so either way, you look at it. And that means the NOCl is increasing because it's on the other side of the equilibrium arrow. It's being produced as those are being used up. I'm a little unhappy with this because I feel like it is incorrect with what the stoichiometry of this reaction would be. So, but that's okay. We'll maybe take a look at that later and correct it. All right. I'm going to let you fill this in because it's just like repetition. You need to make sure that you have those sharp spikes and you don't have S curves. Why don't we want S curves? Because it's wrong. Because it means you have a slow rate of change at first, and you should have you should have the fastest rate of change at the beginning. Okay. Woo! What happened there? Same thing, rate diagrams, no S curves for the same reason. Now, you're going to have a quiz on drawing these diagrams at some point. And if you cannot draw a line that kind of goes like that, if your flat line looks like this, or like this, then you're going to use a ruler for the flat part of the line. Yes? Because this is wrong. That says the concentration goes down and then it goes kind of flat and then it goes up again. This one says it goes up at the end. This one says it goes down at the end. That is wrong. So use a ruler if you need to make a flat line and you cannot just draw a flat line. My son cannot draw a flat line. I don't know if you guys caught that on when he marked your quizzes, but he was like he was like trying to underline something and he was like, and I'm like, what are you doing? Just anyway, I don't know. 21 years old can't draw a straight line. What can you do? I don't know. It just means that like he's made it to adulthood without being able to draw a straight line. I'm like, come on, let's go. Anyway, it's all good. All right, that's it for that one. Stress, changing concentration. Okay, so we're gonna look, stresses make the rates unequal, shifts make the rates equal once again, okay? So here we're changing the concentration of one of the chemical species. If the system is at equilibrium, what can we say about the rate of the forward and reverse reactions? They are, oh, I said that too fast. If the system is at equilibrium, what can we say about the rates of the forward and reverse reactions? They are equal. They are constant. Okay, so we have our forward rate, we have our reverse rate. Now we increase the concentration of H2. What happens to the forward rate? The forward rate increases. Tell your partner why. What parts does your answer need? Ah, particles. What should we say about the particles? More particles. More reactant particles. Ooh, that's even better. Therefore what? Therefore more collisions. Okay, so we see our forward rate increases. What happens to the reverse rate? We've increased the concentration of H2. What happens to the reverse rate? Nothing, because we've done nothing to the amount of products. So which rate is favored, the forward or the reverse? Forward means it's going faster. Forward rate is favored. The forward reaction is favored. This is just looking at the language again around that. If the forward rate is going faster, then the forward rate reaction is favored. As a result of the forward reaction being faster than the reverse rate, The system is now shifting. As it shifts, the following changes to concentration occur. Here, let me write the reaction again. We got H2 plus I2 in equilibrium with 2HI. What's going to happen to our concentration of H2? It's going to go down because the forward rate is using it up faster than the reverse rate is producing it. How about I2? I2 concentration is going to go down because, again, forward rate is using it up faster than the reverse rate is making it, and HI will go up. So now, what is happening to our rates? We had our forward rate, it got a little spike in it. We have our reverse rate. Now, as we are shifting, what is happening to the forward rate? It's decreasing. It's happening to the reverse rate. It's increasing. Can you explain to your partner why? Why is the forward rate decreasing during the shift? What is Anderson doing? Is he being productive? Okay, I'm really glad that's what you're doing.
I'm serious.
Okay, cool.
Forward rate decreases because all of it's getting used up, and it shifts to the right.
All of what's getting used up?
The H2 and the I2, and there's more 2HI, there's more HI concentration. And so the forward rate decreases.
What's happening to H2 and I2? Concentrations are decreasing. Therefore, there are you should always bring it back to what? Collisions. What can you say? If we have less H2 and I2, there's fewer collisions in the forward reaction. The reverse rate increases during the shift. Why? Because we get more and more products. And therefore we get more collisions in the reverse reaction. Also, just in case you guys are wondering, in your answer key, like I actually put in my notes from last year, like they're all in there. So it'll say like 2.2b filled in, and it's all like in there, right? So if you're like, oh my God, I've got these little pictures on my phone, whatever, it is in the answer key as well. I went kind of crazy on this unit with like the filled in business. I thought it might be useful, especially if you're away or something and you don't get a chance to like see it in person. All right, now we're going to draw a concentration diagram of what is happening. When we draw a concentration diagram, you will need to be given the initial or original, oh, that's supposed to be a highlighter, original equilibrium concentrations. If you are not given the original equilibrium concentrations, you can place them wherever you want and just make sure they go the correct direction. Is good? Okay. So, note number one, shifts always follow the rules of stoichiometry, which means you need to pay attention to what? The coefficients. pay attention to coefficients. And that should be familiar to you from rate, because if we have I2 being used up at a rate of 1 mole per molar per minute, HI will be produced at a rate of, if I2 is being used up at a rate of 1 molar per minute, HI will be produced at a rate of 2 molar per minute. Yeah, okay. So if the stress was an increase in concentration, the stressed species is going to get close to the original value, but it's going to end up a little bit above. Everybody is like, because you just got more stuff in there, right? You've put more stuff in, so that concentration has to be higher than it was before. So let's see what that looks like. So we added some, we have H2, we got some I2, we got some HI, okay. We add, this is our concentration, this is time, and at time t, we increase the concentration of H2. What will we see at time t? A spike where? H2. Which direction? Up. Now, I'm going to rewrite this over here so we have it. What's going to happen to the concentration of H2 now? It's going to decrease, yes? Where is it going to end up? Slightly above. So by slightly, that means any amount above, really. Like, you decide, okay? It's not terribly important, just so long as you don't go back to the original level. Now this distance here, I'm going to call it X because I don't know how much it is, okay? What's going to happen to the concentration of I2? It's going to drop also by X because we have a 1 to 1 ratio. So I'm going to draw my little line here. I'm going to say I need it to end at, does that look like the same amount? Sure, we'll say close enough. If you are good at drawing things that look like they're about the same amount, you don't need to draw the little line that says, the little arrow that says X. But let's say that you said, okay, this one's going like this, and it's like this, and then my other one is like this, right? And you're just bad at drawing lines, right? And this distance is obviously different than that distance. But if you label them both X, then I know it's just you being bad at drawing, okay? So if you're bad at making them look the same, then make sure you label them. Yes? Yes. They can cross. I mean, they're not really colliding. It's just the concentrations are, you know, one's becoming more than the other. So now I want my HI. It's gonna have to go up by, and I usually do it like this because I like to be able to see where it should end up. I need to go up by 2x. So it's gonna end up here. And I need to hit my new equilibrium about here. So I need to be flattening there, and I need to yes. Sure. I have rulers though. You can use a ruler. Use one of my rulers. Okay? I mean, like you can see mine is not perfect, but it's straight-ish. It doesn't look obviously like it's, you know, curving once it's flat. Okay? Which direction has the equilibrium shifted? It has shifted to the right. We have made more product. We've used up reactant. We've made product. The system has shifted to the right. Yes. They don't have to. Like if I had made my X smaller, then they wouldn't. Yeah. So if they don't cross, that's okay as long as you have a 2-to-1 ratio in your changes. Yeah. Now, these little X's are going to come in handy later. We're actually going to use them in some math. We're going to set up a little table where we have H2 and I2. I'm just giving you a little preview of what's coming down the line, and we have 2HI. This is our reaction. I'm going to maybe give you an initial concentration. Maybe this is, I don't know, 0.2, 0.2, 0.4, I don't know, just making up numbers. Now you are going to have a change in concentration. Yes? And that change in concentration is going to be, let's just say in this case we had minus X, and plus 2X. And you will finally end up with an equilibrium concentration. And in this case, this would be 0.2 minus X. This would be 0.2 minus X, and this would be 0.4 plus 2X. Please excuse the fact that these numbers don't match what's on the graph at all, because they really don't, okay? But that's where we're gonna get to eventually. You can just kind of ignore that for now, because we're not there yet. That's section 2.3. But look what we've made. We have made a rice table. Most people call them ice tables, but often people will forget to write the reaction. And one of my students one year, about 10 years ago, maybe 15 years ago, was like, well, why don't we call it a rice table? And I'm like, oh, that's so good. Because then we remember to write the reaction, right, as well. I also like them being ice tables because then they're cool, but, you know, can't have everything. All right, we got like 3 minutes left, is that right? 2 minutes? What do I want you to do here? Actually, you know what I'm gonna do? I'm gonna go way off script here. You are going to, your homework, you're gonna get an acid-base book. You're gonna get an acid-base book, and you're going to do 4.1a and 4.1b. Nope. And you're like, what is this of which you speak, Ms. Spence? Oh, is it in the stuff in the back? Yes, it's the stuff in the back. Why did I say no? I don't know. You're gonna go here. You're gonna one of these, and then you're going to put it together. Okay? And you're going to be watching a video for the first one, you're going to be watching a video for the second one. All right? That way we can learn together. And yeah. Would anyone like this one? Would you like this one? Since it's here, might as well. Answer keys will be coming for this shortly. Yes. We will be doing 3, but this is like very good for independent learning. So I'm giving you a little independent learning.